Hello, 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 the time has come that you're going to see your complete final physics of the solution to the rotating disk problem. Math is the language of physics. I assume that you have watched my first video, the first solution video. It's a must that you do that. You will then know why kinetic energy is not conserved. You will then also know why angular momentum is not conserved. And you will then also know why in the final state, which I have called jokingly the equilibrium state, why in that final state, when the angular velocity of omega of disk 1 is no longer changing, and why the angular velocity of disk number 2 is also no longer changing, that in that equilibrium state, omega 1 R1 equals omega 2 R2 in magnitudes. Of course, omega 1 and omega 2 are both vectors and they are in opposite direction, but that's not important now. In magnitudes, the two values are the same. And if you have any doubts about that, watch again my first video. All of you will remember, of course, I hope, Newton's law, F equals ma. And if we have a motion, linear motion, one-dimensional, just for simplicity, then the velocity at time t is the velocity at time 0 plus or minus at. T is time. Think of them as one-dimensional. You can think of them in the x direction if you prefer that. If Vt minus V0 is negative, it means A was negative. If Vt minus V0 is positive, then A was positive. So now you see here the equivalents for rotating objects. We always replace the mass by moment of inertia, the force by torque, and the linear acceleration by angular acceleration, which we call alpha. So alpha is d omega dt. Just like A was dv dt. So in parallel to this equation, we can write down now here that the angular velocity at time t is the angular velocity at time 0 plus or minus alpha t. Alpha is then the angular acceleration and t is the time. We know that at time t equals 0, disk number 1 stands still. So omega 0 is 0 for disk number 1. We know that disk number 1 will spin up, and it will spin up in clockwise direction. I will therefore use for disk number 1 alpha positive, because I'm only interested in the magnitude. I will remember, believe me, later I will remember that disk number 1 is spinning in the clockwise direction. Let's now go to disk number 2. For disk number 2, omega 0 is omega, and it is omega in the counterclockwise direction. And it will remain in the counterclockwise direction. It will spin down. So that means that when I use this equation for disk number 2, that I have to use for alpha a negative value. In both cases, for disk 1 and disk 2, I will find the magnitude of omega at time t. But it's important that you realize now why I'm going to put a plus sign in for alpha on disk number 1 and why I have to put a minus sign in for disk number 2. Now, let's first go to disk number 1. Tau equals I alpha. What is tau? So tau is the cross product between the position vector from the center of the disk to the frictional force F. And they are perpendicular to each other. So I can forget about the sign of the angle. So it's clear that tau is simply R1F. The moment of inertia of a solid disk rotating about its center is 1/2 mr squared. So this speaks for itself. So now, if I apply this equation, I can calculate what alpha 1 is. You get a 2f divided by m1 r1. And so similarly, alpha 2 for number 2 is of course the same in magnitude, except that you now get m2 r2. However, when we're going to use that, we have to use this negative sign. And we can use that as a positive sign. Disk 1 is spinning up, disk 2 is spinning down. So we apply this now to disk number 1. Omega t, omega 0 was 0, is this alpha times t. You see, I just put a t here. And at equilibrium state, that is omega 1. So this must be omega 1. So ft is this. Now you may say, well, we're stuck. We don't know what capital F is. If I push hard, F will be high, because the normal force will be high. If I don't push very hard, then F will be very low. Well, that's the wonderful thing about this problem. You will see very shortly that I can eliminate capital F times t. And what that means, if I can eliminate it, that the final state, which I call equilibrium state, that omega 1 and omega 2 are completely independent of the force that I, Walter Lewin, apply. If I use a strong force, I push them together with a strong force, well, then it won't take very long. T will be small before we reach the equilibrium phase. If I push very softly, well, then T will be very long. It will take a long time to reach equilibrium state. But the beauty is, since Ft can be eliminated, that I can even push hard at some moments in time, then not so hard a little later, then harder again, and then not so hard. It makes no difference. The final result in the equilibrium state will always be the same. Okay, so now we're going to use this equation for object number 2, and I've explained to you why I have to use the negative value for this alpha. So, if you're ready, then I'm going to change the position of my camera. Alright, well, that's very good. You can see it quite well, I hope. So, omega t is omega 0, which for disk number 2 is omega. And then we get here minus alpha 2 times t. And that is omega 2. Because that is the moment we're interested in. That omega of disk number 1 and omega of disk number 2 are no longer changing. And now look at the miracle. Do you see the ft there? Do you still see this ft there? Ha! So, what am I going to do? It's obvious. I am going to replace this ft by the one that we just calculated for this one. Thereby, I eliminate it. So we know that this has to be omega 2. We replace ft by omega 1 over 2 times m1 r1, and now you see here an equation with no f and no t anymore. I repeat myself. The final result, equilibrium state, is independent on how hard I push. It only determines how long it takes before I equilibrium state. We're almost done now, because omega 1 r1 is also omega 2 r2. So I can replace these. m1 divided by m2 is r1 squared divided by r2 squared. Remember, the disks have the same thickness and the same material. So the only difference is the radii, And so this ratio is the ratio of the radii squared. And so out pops our first result. Omega 2, and I put the absolute signs here to remind you that we do know that it is in the opposite direction of omega 1, and we also know, we remember that it is in the counterclockwise direction. So that is omega divided by 1 plus r1 over r2 squared. So how about omega 1 now? Well, that's a piece of cake. If I have omega 2, then all I have to do is multiply it by r2 over r1 and I get omega 1. So, if you're ready for that, I have to change the position of my camera. And that changes, this takes a little bit of time. Yeah, we're almost there. There we go. So, this is the equilibrium state. We already calculated omega 2, out pops omega 1. And now comes the remarkable thing. Omega 1 and omega 2 are totally independent of mu, the friction coefficient, independent on how fast I push, how hard I push, and independent of the time it takes. If I push hard, t will be short. If I don't push so hard, t will be larger. It's independent. That's remarkable, isn't it? It's nice to do some consistency checks. We always do that in physics. If R1 were R2, it should be immediately obvious to all of you, I wouldn't have to explain that the magnitude of omega 1 must be then omega 2. For the simple reason that that's the equilibrium state. I put the absolute sign here because we do remember, of course, they are in opposite directions. What is not so obvious, that if you substitute in this equation R1 is R2, it's not so obvious that you find 1/2 omega. But that's a detail for me now. So if you substitute in omega 2, R1 is R2, you find the same value as here, and in both cases you find 1/2 omega. You can do another consistency check, which physicists always do. Suppose you make R2 much, much larger than R1. If you look at these equations, and I invite you to do that, you will find that omega 2 is then approximately omega. And that's what you expect. Think about it. That's really what you expect. And if R2 is much, much smaller than R1, then you expect that omega 1 will be 0. Try that. That's consistent with our equations. Now I want to demonstrate to you that angular momentum is not conserved and that kinetic energy is not conserved. And I do that, you can do that for any ratio of R2 over R1 that you please. I prefer to take R1 equals R2, because I don't want to get into another mess of mathematics. I simply want to show that if I take R1 equals R2, that very clearly kinetic energy is not conserved and angular momentum is not conserved. So, all right. So look at this. So R1 is R2. So omega 1, the magnitude, is 1/2 omega. And omega 2, the magnitude, is also 1/2 omega. Omega 1 is clockwise, we've discussed that many times in the equilibrium state, but omega 2 is in the same direction as omega, which is counterclockwise. What was the angular momentum when we started? Well, that was I omega. You will say, no, it was I2 omega. Yeah, sure. But if R1 equals R2, the moment of inertia of both this is the same. So I might as well call it I. So it's I omega. In the equilibrium state, which I call here after, that's really the equilibrium state, disk 1 is I 1/2 omega, and disk 2 is I 1/2 omega. But now it is important that you realize they are in opposite directions. So there has to be here a minus sign. And so it's 0. Isn't that wonderful? So all the angular momentum that was there is now 0 for this combination R1 equals R2. Let's now look at the energy. The energy, when the problem started, is 1/2 I omega squared. In equilibrium state, it is 1/2 I times omega 1 squared plus 1/2 I times omega 2 squared. Now signs do not matter because the square of a minus sign is still plus. So now there is a plus sign here. And so you see that the total kinetic energy afterwards for this combination is half of what it was before. So you've lost 50% of your kinetic energy. So I hope I have convinced you that angular momentum is not conserved, Kinetic energy is not conserved. And that's why this problem is not as easy as many of you have thought. If you watch video 1 and you watch this one also, you should be able to go over the whole problem again, think it through, and you probably have learned something very basic in Newtonian mechanics. And therefore, I'm sure you would want to be friends with me again. Have a nice day and take care.